So we're finishing up the chapter. There we go. So chapter 19, the spectrophotometry, instruments and applications, but we're right now still looking at what happens when a molecule absorbs light. This is part 3 of that conversation. Although technically what we're looking at is how does a molecule get rid of the energy that it got when it absorbed light. We're going to be looking at how the energy is leaving. So this was the last slide of the previous video, that after a molecule absorbs energy from microwave, infrared, visible, UV, whatever, in order for it to go back down to the ground state, to its lowest energy state, it has to emit this energy. This energy has to leave. It has to give it away for it to go back down. Okay. So if we have an electronic transition that occurs, then that light needs to be, or that energy needs to be emitted down to the lowest vibrational and rotational level of the highest excited state. So in this example, the excited state we're looking at are singlets. That's S1. So it's going from S0, which is the ground state, and then an electron was promoted to S1, which is the singlet state, and that's when we see an electron. When it's promoted, we see that they have opposite spins at each location. The triplet state is when they're both pointing up. Okay, so it would be that the electrons are still in these places, but it's going to lose enough energy to get to the lowest vibrational and lowest rotational state of this singlet, the highest singlet 1 or S1 state. That's called the radiationless transition because there's no light involved with that. What it's going to do is it's going to collide with other molecules, probably the solvent if it's in a solution, transfer the energy that way. So basically it's transferring its energy through collisions. There's no light that's being let out. So it absorbed light, sure. But when at this point, when it's emitting energy, it's not using it's not giving away light as its way of emitting. Okay. So I want to show us a picture. This is a picture of pretty much all the scenarios for what happens when light is shined at a molecule and absorbed. So down here at the bottom, that big black line is the ground state. Any arrows pointing up are when light is absorbed. Any arrows pointing down are when energy is emitted. The type of energy depends on the scenario, okay? But what we see here is if we have a molecule that absorbs light that is in the microwave or the infrared spectrum, then it cannot go to a singlet or a triplet excited state. It stays in the singlet state, which just means the electrons are opposite spins, which would be true in its orbital, but it moves to a higher vibrational or rotational state. Okay, so like that red arrow would be IR or microwave, and so it's going to higher energy, but the electrons are staying where they're at. And so that's the up arrow. Now the down arrow have these squigglies. This guy, I guess I should change colors. And the symbols R. R stands for radiationless. So that means collisions. So it's getting back down to the ground state by just smashing in, using its vibrational and rotational energy to be like a hyper child on sugar and smashing into the walls, smashing into everything around it. So it's losing its energy because it's colliding with other things, and that energy is being transferred to other things. Okay. Now, if we have enough energy for it to be excited to a higher electronic state, so if we're talking UV vis, then this arrow going on right here, I guess I'll try to trace it sort of ish in purple, would be we shined UV visible light. So the electron was excited. Okay. Now in this scenario, the electron was excited in the singlet state. Okay. So when it moved to the higher energy level, the spins stayed opposite. So in order for this scenario to get back down to the ground state, it takes a little bit more effort than just colliding with the solvents, because we've got other things. The electron has to actually move. So one way, I guess I'll do a different color here. Do green. For that to get home, which by home is the ground state, is to do a radiationless transition down to the lowest vibrational and rotational spot in the singlet state. So the electron is still in a higher energy level, is in a higher molecular orbital, but it's at the lowest rotational and vibrational amount of energy that it has at that point. Then what it can do is it can do what is called an internal conversion, where the electron is at the lowest vibrational and rotational state of the singlet state, so it's up higher, and it's going to move to the vibrational / rotational state of the ground state that has the exact same energy. So pretty much the electron is returning home, but when it does so at this point, internal conversion has not lost any energy. Okay, and then it can just do a radiationless transition, collide with its friends to get back down to the ground state. So that is one way for an electron that has been promoted to a higher level singlet state for it to get back to the ground state. Radiationless transition to the bottom of S1, an internal conversion from S1 to S0 with the same amount of energy, and then a radiationless transition down to the bottom. Okay, let's look at scenario 2. Scenario 2. So I'm at purple. In scenario 2, we would have... did you not go to orange? I meant for you to go to orange. There. For it to do a radiationless transition down to the lowest singlet state. Then it can do what is called an intersystem crossing, which means the electron is going to stay in the excited energy level, but it's going to change its spin to where now both electrons in the lower orbital and in the higher orbital are both pointing up. So basically, the pointing down became pointing up. That's called an intersystem crossing because it changed from a singlet to a triplet. Okay. Then what can happen is that, so it's an excited triplet state because the electron is still in a higher energy level. It can do a radiationless transition down to the lowest vibrational and rotational state of the triplet 1. And then it's going to do another intersystem crossing because it's going from triplet to singlet back to S0. So now we're at the ground, the singlet state 0, but we're at a higher vibrational or rotational level. And then it can do radiationless transition down to the bottom. So the first scenario that I did in green is called internal conversion. The second scenario is called intersystem crossing, but it just has more steps. That one, we'll do navy. Okay. So we've got 2 more scenarios. So once again, we shine UV vis light at it. It moves up to a singlet state. It can do a radiationless transition down to the bottom of the singlet state. And then what it can do from there is go straight to the bottom by letting off a photon, by letting off light of some wavelength and frequency. And that light, that scenario is called fluorescence. So things that fluoresce are things that let off light. Think like glow sticks, stuff like that, okay? So they absorb light, or they absorb energy from the light around them, but they're going to lose some of their energy to do a radiationless transition to get to the bottom of S1, and they're going to let off photons, and it's called fluorescence. Okay. Now, notice the size of the arrow pointing down and the size of the purple arrow pointing up are not the same. So the color of light you shine at it to excite it, and the color of light that it releases are going to be different colors of light because they have a different amount of energy, so a different wavelength, a different frequency, because some of that energy is lost by the radiationless transition. Okay, so last scenario. We shine UV vis light. It's promoted up to the singlet state. It does a radiationless transition down to the bottom of the singlet state. Then it does an intersystem crossing to the triplet state. Okay, and then it does a radiationless transition to get to the bottom of the triplet state. Now, instead of doing another intersystem crossing, it is going to then release a photon of some wavelength and frequency, and that is called phosphorescence. So it's letting off light as well. Now, notice The phosphorescence arrow is a different size than the fluorescence arrow, which is a different size than the purple arrow and how much energy it absorbed. So the color of light that it releases is going to be different than the color of light we shined at it to make it excited in the first place. Fluorescence photons are going to have more energy than phosphorescence photons, because if you look at the size of the arrow, isn't the fluorescence arrow longer than the phosphorescence arrow? And that's true because when it does the intersystem crossing, when we're doing phosphorescence, it's going to do another radiationless transition to get to the bottom before it lets off the photon. So what I would be prepared to do with this is be able to map out these scenarios. Talk me through different ways that a photon, when photons are being shined at a molecule and it's excited to a higher state, how can it relax back down to the ground state? So we had the scenario where it was IR and microwave, so it just did a radiationless transition and got back to the bottom. Then we had one where it was UV, we had several where it's UV vis, so it's excited, and then it does internal conversion to get back down. Then our second one was to do intersystem crossing, radiationless, intersystem crossing, radiationless. Then we saw radiationless to fluorescence, which is going straight from the singlet state. And then we saw radiationless over to intersystem crossing, down to radiationless, and then letting off a photon, which was phosphorescence. So know these paths. What is here is me talking through these paths with words. I use the symbols IC for internal conversion, and then ISC for intersystem crossing. And it might seem like gibberish, but all these are the scenarios. So this was talking through internal conversion and intersystem crossing. And these are converting light into heat, meaning we don't see any light come out of the molecule. All of the energy that was absorbed from light comes out as collisions with the solvents, so that's where we see the heat. Now, we also have the scenarios where the molecule released light. So fluorescence is when it's releasing light from an excited singlet state, and phosphorescence is when it's releasing light from an excited triplet state. And phosphorescence has less energy light than fluorescence. Because of that picture, you can see that the arrow was smaller. So which one of these scenarios happens depends on the molecule and the conditions, meaning the temperature and the pressure. So I'm saying that between internal conversion, intersystem crossing, fluorescence, and phosphorescence, which one happens depends on the situation. Okay. And I'm not going to be asking you to tell me which one's going to happen. I'm going to ask if you know these and can explain them to me. I can tell you that fluorescence and phosphorescence is pretty rare. That doesn't happen very often. We don't see a lot of things glowing. There are things that fluoresce and phosphoresce, but most of them go back down to the ground state using internal conversion or intersystem crossing. Think about the molecules that you've put into a spectrophotometer. They had to go through this process because we shined light at it, so they got excited. And the spectrophotometers we used were visible or infrared, so they were all either internal conversion or intersystem crossing. You didn't see that happening by looking at it. The molecules that we've tested did not do fluorescence or phosphorescence. Okay, so there's that picture again. What I would be prepared to do is looking at that picture, if I took off all the words, but I left on the symbols. So like S0, S1, T1, took off the arrows, took off the words, and had you map out to me the different ways for a molecule to get back down to the ground state. That's what I would be prepared to do if I were you. So I would take off the words. I'd take off most of the arrows. I'd probably only leave the up arrow, which is this one. And then you would have to map it out to me to get back down to the bottom. So since we've talked about fluorescence and phosphorescence, there's a part of spectrophotometry that we haven't talked about yet, but we couldn't talk about it until we talked about fluorescence and phosphorescence. And that's called, well, first of all, luminescence is the category for fluorescence and phosphorescence. It's whenever light is emitted from an excited state of a molecule. Okay, so it got to an excited state and it lets off light. Okay, so luminescence is measuring the luminescence, measuring the light that's being fluoresced or phosphoresced, is more sensitive than absorption. So the scenario, the way this was explained to me, and it actually is discussed this way in our textbook as well. So the difference between luminescence and absorption, in both of them we're measuring light, but in absorption, we're shining a crap ton of light at a molecule or at a sample. It's absorbing some of that light, and then we're measuring how much light did not get absorbed. So thinking about that in a different way. It's I take a dark room with no windows, no doors, whatever, or closed doors, light a bunch of candles, blow out some of the candles, and measure how much light was there before I blew them out and how much light was there after I blew them out. There would be a difference. I'd be able to measure that. But that's absorption. Okay. Luminescence would be if I'm only measuring the light that it is releasing, that is emitting as it relaxes. So that would be like starting with no light, because before you excite it, there's no light being released. And then you light a candle. Well, we're able to measure, like we're able to see that one candle being lit has such a bigger impact than having 600 candles and blowing out 40 of them. We would see that difference in light. There's a little bit less light being released from 560 candles than from 600 candles, but still it's way easier to take a dark room, light one candle, and see that difference. So luminescence, if we have a molecule that does fluorescence or phosphorescence, we're not going to measure its absorption. We're going to measure the fluorescence and the phosphorescence, because that's way more sensitive, meaning it can get all the way down to, I could just have one molecule in my sample, and fluorescence and phosphorescence can pick up the fact that there's only one molecule. That's why this is so important and used in so many other applications. They use tracers when we're looking at biological processes that have molecules that fluoresce and phosphoresce, because they're able to track that tracer that they attach to some sort of biologically active molecule and see where it moves in a living system, because it can measure that one molecule that's letting off light. It's just super cool. Okay, so in luminescence, we're measuring the light that's emitted, not the light that's being shined at the sample. And so again, we'd have to have a light source to excite the molecule so it gets to that higher energy level, and then we let the molecule let off its light, and we measure the light that's being emitted. So the wavelength of light that we shine at the sample is going to be different than the wavelength of light that they release. So the emitted light, the fluorescence or the phosphorescence, are always going to be longer wavelengths, which means lower energy. Okay. So here's an example of what, if we were doing emission spectra, like an emission spectrophotometer would look like. It has all the same pieces as the absorption spectrophotometry. They're just in a different order, and there's a couple more of them. So we have a light source. There's our light bulb. Lots of wavelengths. And then we have a monochromator. It's going to filter out all the wavelengths except for the lambda max, which they're calling the lambda excitation, which is the wavelength that excites the molecule. It's the same thing. Okay. And then here's our cuvette with our sample. Okay. Now, that sample, once it gets excited, it's going to release its own color of light. So luminescence, which will either be fluorescence or phosphorescence, is letting off light. And then we have an emission monochromator, which is just to filter out to make sure that the wavelength of light that we want to measure, in case there's contamination or something, is in there. And then it sends just the emission wavelength to the detector. Notice that there's a 90-degree angle right here, because there's going to be light that goes through the cuvette off to the other side, and we don't want to measure that. So it's going to go into it's going to be pointed at nothing. So there's a right angle, a 90-degree angle, so that to make sure that none of this light gets to there. We don't want any of the light coming from the light source to get to the detector. We only want the light being released by the molecule getting to the detector. Okay. So, mentioned this, but the wavelength of the excitation, like of the monochromator, the first monochromator that filters it, and the wavelength of the emitted light are going to be different. And so we get a graph of the excitation wavelength versus the luminescence wavelength. So this is what we would see. We can see the difference between the wavelengths of light that, in this case, anthracene fluoresces versus the wavelengths of light that it excites. And so these would be the ones that they used for that. So that takes us through the end of chapter 19.